Welcome to our first Zoom lecture, and we're going to focus on evaluating limits graphically and numerically, and then we're going to discuss the average rates of change, also known as slope, for those of you who took Algebra 2 in high school. So let's look at our first set of problems. We have a piecewise defined function here. I don't know exactly what the functions are. I do know that this one in the middle appears to be a quadratic that's concave down. This function here is linear, and I'm not sure what this one is over here. I could describe some of its characteristics. That's really not the point of this exercise. What we want to do is we want to go back and we want to evaluate the limit as x takes on different values. In other words, as x gets closer to a particular value from either the left or the right, or from both directions, what value is y approaching? That's what we're trying to do here. So let's look at A. A says that x is approaching 0 from the left. Now, how do I know it's from the left? Because if you look at the index next to the 0, you can see a minus sign. So that tells me that x is approaching 0 from the left. So if you look at the graph, I can see that x is getting closer and closer to 0 from the left. And the question is, as x gets closer and closer to 0 from the left, what value is y approaching? Well, let's look at some of the values as x approaches 0 from the left. When x hits -2, it appears that the y value is here, just a little bit bigger than -1. And then as x gets to, let's say, -1.5, it appears that y has hit -1. And then it starts to increase, right, as x approaches 0 from the left. For example, when x takes on the value -1, we can see that y has gone up just a little bit. And as x gets closer and closer to 0, we can see that y is approaching the value 0. So the limit as x approaches 0 from the left is going to be 0. So let's look at part B. Bring the graph up here. Part B says that we are going to approach 0 from the right, as designated by the plus sign. And again, as we approach 0 from the right, coming in from this direction towards 0, what is happening to the y values? If we look at the y value and x hits 1, we can see that the y value is here at 1. But as x gets closer and closer to 0, we can see that the y values are getting closer and closer to 2. So as x gets closer to 0 from the right, y approaches 2. So the limit would be 2. Let's look at part C. Part C does not have a minus sign nor a plus sign, so this means in general, as x approaches 0 from both directions, what is the limit? Well, coming in from the left side, we hit 0 for the limit, and as we approach x from the right side, the limit is 2. Well, since those limits do not agree from both directions, we would say that the limit in general does not exist. And depending on the textbook, some would simply write DNE. Some textbooks have different notations, but we're going to say that since the limits do not coincide, or they're not the same from both directions, we would just simply say that the limit as x approaches 0 does not exist. Let's move now to part D. Part D says that we are approaching 2 from the left. Well, if we're approaching 2 from the left side, that means that y is moving down toward the value -2. The closer you get to 2 from the left, the closer y converges to the value -2. What about the limit as you approach 2 from the right? This would be part E. Well, if you're approaching 2 from the right, x is moving in this direction. And if y follows suit, it's going down toward the value 0. So the limit as x approaches 2 from the right would be 0. And again, part F wants to know, what is the limit as x approaches 2 in general? Well, since the limit from the left is -2 and the limit from the right is 0, the limit in general as x approaches 2 does not exist. Part G. Part G, we have the limit as x approaches 4 from the right. I'm sorry, from the left. So as you approach 4 from the left, x is moving in this direction, which means the corresponding y values are moving in this direction from the left. Notice that the closer you get to 4 from the left, the closer y is taking on the value 4. So the limit as you approach 4 from the left would be 4. And if you are approaching from the right side, coming in from this direction, let me change colors here. If we are approaching 4 from the right side, then the y values are coming down toward 4. So the limit as you approach 4 from the right is also 4. And since those limits agree from both directions, the limit in general as x approaches 4 would be 4. So this is an example of how you would evaluate limits from the left, from the right, or in general using a graph. So let's look at another example. Let's look at this piecewise defined function here. Now, the reason this is piecewise defined is because this is a function that is comprised of several other functions, just as the previous function was. And in this case, we have a function that is continuous because it passes the pencil test. In other words, if I start on the left side, as far as I can see, I can actually trace this function without having to pick up the pencil. So that is a continuous function. If you go to our previous function, we could not do that. In other words, if I wanted to trace the other graph, if I wanted to go from left to right, notice that when I get to this position, I would have to pick up the pencil in order to continue. In fact, I would have to pick up the pencil at least twice. No, here again, we have to pick up because of this discontinuity. So this function here is discontinuous. It's not continuous. This function on the right side is a continuous function because it passes the pencil test, whereas the previous function does not. So let's pick up here. Let's look at this continuous piecewise defined function. And let's talk about the limits as x takes on different values. Well, let's look at the value -3. Notice that as x approaches -3 from the left, the y value approaches 0. And if x approaches -3 from the right side, y is still approaching 0. So the limit as x approaches -3 for this function would be 0. What about when x is approaching 0? Well, if you're approaching 0 from the left, notice that y is approaching the value 3. And if you are approaching 0 from the left, notice that the y values, again, are climbing toward y is equal to 3. So the limit as x approaches 0 would be 3. Let's look at a concept known as limits at infinity. Notice that if we are approaching 3 from the left, we're coming in from this direction. Look at where the graph happens to be. Notice the graph is below And the closer you get to 3 from the left, the more negative this graph becomes. In other words, as you approach 3 from the left, the limit would be negative infinity. But if you are approaching 3 from the right, you're coming in from this direction toward 3 from the right. Notice that y is going up in the positive direction, which is positive infinity. So the limit as you approach 3 from the left is negative infinity, but the limit as you approach 3 from the right is positive infinity. Therefore, the limit itself does not exist. We can also evaluate limits using algebra. Sometimes we can use direct substitution. For example, suppose you have a polynomial expression that says, in this example, evaluate the limit as x approaches 2 for the given polynomial expression 2x squared plus 3x minus 5. Well, as long as I can substitute the 2 directly into the equation without violating any rules of algebra, I can do that. In other words, I'm going to let x take on the value 2. So 2 times 2 squared plus 3 times 2 minus 5 would give me 9. So the limit as x approaches 2 is 9. Is direct substitution always allowable? The answer is no. If you look at the second example here, notice that if I plug in 2 for x, the denominator would zero out, which is not allowed. Division by 0 is not allowed. So in order to solve this problem, we would have to do some simplification. Notice that x squared minus 4 is actually a difference of squares. And you may recall from high school algebra that if you have a difference of squares, you may factor this way. In other words, x squared minus 4 would be x plus 2 times x minus 2 you may need to go to some YouTube videos and investigate or review how to factor differences of squares, because that will be an issue in your homework problems in my math lab. But anyway, if we factor x squared minus 4 to become x plus 2 times x minus 2, notice that the x minus 2 in the denominator will cancel out the x minus 2 in the numerator, which leaves you x plus 2. In other words, x squared minus 4 divided by x minus 2 simplifies to x minus 2. Now you can use direct substitution. In other words, you can plug the 2 directly in, and that would give you the limit of 4. We also have some tricks to evaluating limits, and we will get into those momentarily. But first, let's look at one more example of looking at a limit by analyzing the graph. If you look at this problem here, notice that as x gets larger, in other words, as x approaches infinity, the y value is actually leveling off. And it's leveling off at the value 2. And as x approaches infinity, negative infinity, in other words, as x gets smaller and smaller, look at what's happening to the graph. It is getting small, that's true, but it's also leveling off toward negative 2. Now the graph will never actually touch 2 or negative 2, but that's the limit, because that is what the y value is approaching as x approaches either infinity or negative infinity. Since y can never equal negative 2, in other words, the graph just simply gets closer and closer to negative 2, that would be considered a horizontal asymptote. Also, y is equal to 2 would be a horizontal asymptote near the top. Okay, So here's some tricks to familiarize yourself with, and they can be used to quickly evaluate limits. The first one says, if you are looking at limits at infinity, these only apply to limits at infinity. So this problem here, we're looking at the limit as x approaches negative infinity for this given expression. Well, the first trick says, if the degree of the numerator is less than the degree of the denominator, the limit will be 0. Okay, so let's take a look at that. Notice that the degree of the numerator happens to be 2, and the degree of the denominator happens to be 3. Well, according to this trick, since the degree of the numerator is less than the degree of the denominator, the limit is 0. That's not a bad trick to memorize. If you get into the textbook, you will see that there are other ways to derive the 0. I just want to show you a couple of tricks here. The second trick says, if the degree of the numerator is equal to the degree of the denominator, then the limit is the ratio of the coefficients of the highest degree. So if you look at the second problem here, notice that the degree of the numerator is 2, the degree of the denominator is 2, and since those are equal, then all you have to do is focus on the coefficients for those terms. Notice that I have a coefficient of 2 here and a coefficient of 3 here, which will carry over to the solution, 2 over 3, 2/3. So the limit as x approaches infinity for that given expression is 2/3. And I was able to calculate that simply by using this trick here. So whenever the numerator degree is equal to the degree of the denominator, just look at the coefficients and that will give you your answer. And one last trick. If the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. So here we have a degree of 2 in the numerator and a degree of 1 in the denominator. So since the degree of the numerator is greater than the degree of the denominator, the limit does not exist. And we have been writing does not exist. If there's no confusion, you could use the infinity symbol as well. By the way, most of you are probably used to using TI-81s for Nashville State. There's a program out there you may be familiar with called Desmos. You can download the app to your phone or you can use a desktop platform. But Desmos is an excellent tool for graphing, especially complex equations and those types of things. So consider downloading Desmos to your cell phone or maybe to your desktop or both. And there are plenty of YouTube videos on how to use Desmos, but it's an excellent way to graph equations and evaluate limits. The final topic for this first lecture is average rates of change, also known as the slope. For example, if we have the function 2x squared minus 1, and I'm looking to find the average rate of change of the function as x changes from 2 to 1. Well, what you're going to do is you're going to evaluate the y value when x is 2, subtract from that the y value when x is 1, and then simply divide by the difference, 2 minus 1. And if you follow that formula, you will see that the average rate of change is 6. So how would that look like from an algebra perspective? Well, if I were to draw a graph, and I were to plot points, this is going to be a quadratic that has an intercept at y is -1. Let me change colors here. The graph would look something like this. Obviously, I'm not using Desmos, or it would look a lot more professional, but hopefully you get the idea here. So the picture would look something like this. And I've got two x values I'm concerned about. The first one is x is 2. The second is x is 1. Well, if I plug 2 directly into the function, 2 squared is 4, and 4 times 2 is 8, and 8 minus 1 is 7. So if x is 2, y should be 7. So I'm going to plot the point here, 2, 7. And now let's look at the 1. Well, if I plug 1 into the function, 1 squared is 1, 1 times 2 is 2, and 2 minus 1 is 1. So the point 1, 1 would be on the graph, and I will put it here. So again, the average rate of change as x takes on two different values is simply going to be the change in y over the change in x, also known as the rise over the run. Well, notice that the rise is this distance here in yellow, and we will say that the run is going to be this distance here in green. In other words, that's the change in y over the change in x. So what is the change in y? Well, if you are here when y is 7 and you drop down here to where y is equal to 1, the change is going to be 6. That's the change in y. And in calculus, we simply say delta y. That's the change in y. What about the change in x? Well, we went from x is 1 to x is 2. So that's only a displacement of 1. So 1 would be our change in x. So the change in y over the change in x, also known as the rise over the run, is simply going to be 6 over 1, which is 6, which happens to be the answer we got. The second part says to evaluate the average rate of change or the slope as x takes on the values 0 and 3. And again, we just do the exact same thing. And in this particular example, we happen to get 6 again. Here's a little note here to think about. Many students are concerned about determining which value of x should be used first. If you happen to rework the problems and switch the x values, you will get the same answer. I would say always be consistent. In other words, if you want to let x take on the value 2, and then let x take on the value 1, as we did here. First x is 2, then x is 1. And look at on the bottom, again, we used 2 and 1. I could have used 1 here. Let me change colors here. I could have used 1 at the beginning and then 2 here. If I had done that, then I would need to put a 1 in the leading position here, followed by a 2. So the order does not matter as long as you are consistent. And the last thing we're going to talk about is the algebraic definition of derivative. At first, this expression is somewhat daunting. It can be, depending on the nature of the problem. The derivative is actually the instantaneous slope, the instantaneous rate of change. Notice that when we did the average rate of change, we had to have a beginning and an ending in order to calculate the average rate of change. But with the derivative, or the instantaneous rate of change, we can figure out the slope of a line at a particular value of x. We'll get more into that next week. But for now, realize that the equation for finding the instantaneous velocity or the derivative is the limit as h approaches 0, and you have to evaluate f of x plus h minus f of x over h. And let's do a quick example here. If I take on the expression y is equal to x squared minus 3, I'm going to try to draw this. So let's let the, we'll let this be the y-axis, and of course the horizontal line would be the x-axis. And just for the sake of argument, let me plot this very quickly. This is going to be a quadratic expression that has an intercept at y is -3. So it's going to look something like this. It's a parabola. And I'm looking for the derivative or the slope at a particular value on this graph. For example, let's say that I would like to know the slope when x takes on 3. Well, if I plug in 3 for x, 3 squared is 9, and 9 minus 3 is 6. So if x is 3, then y is 6. So that's going to be our point here. The question is, what would be the slope of the tangent line to the curve when x is equal to 3? In other words, if I had a straight line coming down that only touched this graph when x is equal to 3, I'm going to say these touch here. What would be the slope of this line? If I want to know the slope of the line when x is 3, first I need to figure out the general equation for the slope, or the derivative. So I fall back to this formula here, f of x plus h minus f of x over h as h approaches 0. So f of x plus h means that I have to go back into the original equation and I have to substitute in x plus h everywhere I see x. Notice that I have x here in the equation. And according to the formula, I first have to introduce x plus h in place of x. So that's going to give me the limit as h approaches 0 of x plus h to the power of 2. And of course, the negative 3 or the minus 3 has to go along for the ride. And according to the formula, I now have to subtract the function. Well, the function is x squared minus 3. So I have to subtract off f of x. If you take x plus h to the power of 2, that's x plus h times x plus h. And if you FOIL that, you will get x squared plus 2xh plus h squared minus 3 minus x squared plus 3, because a minus and a minus is a plus. If you simplify this down, you can eventually plug in 0 for h. Notice that we could not plug in 0 from h at the very beginning because that would have given us a 0 in the denominator. But now that we have simplified this down to 2x plus h, there is no harm in substituting 0 for h, and the derivative is 2 times x. So if you want to know what the slope of the tangent line is for any particular x value, substitute that value in for x. We are worried about the slope when x is 3, so 2 times 3 would give us a slope of 6. What about the slope when x is 0? If x is 0, notice that we would have a horizontal line here that would touch the graph only once. Well, if we plug in 0 in place of 2 times x, that would give us 2 times 0, which is, of course, 0. Notice that if x takes on any negative value, notice that the slopes are also negative, right? Because you're going down from the left. So that is an overview of limits and an overview of the algebraic definition of derivative. Thank you.